other situations, and there are also quite numerous these situations when exact wave function cannot be faithfully approximated by just a single Slater determinant or single mean field wave function, and it needs more Slater determinants, more electronic configurations to describe it even at the lowest level of approximation, right? And one of the situations is bond dissociation. In such a case, standard Relay Schrödinger perturbation theory is not valid, and this expansion, if we try to build the whole perturbational series for the correlation energy, we may see that it is divergent. And situations when it is required to combine several electronic configurations to describe even approximately the exact wave function are known as situations where the non-dynamic or static correlation is present. So single reference description, there it is dominated by single electronic configuration, the exact wave function, and dynamic correlation, which can be evaluated from perturbational methodologies such as coupled cluster or MPN methodologies. This is one, let's say, extreme in molecular physics. Another extreme is non-dynamic correlation, when we require several electronic configurations in the lowest order approximation to the wave function. And in fact, non-dynamic correlation is quite ubiquitous. It can be met in organic chemistry, in inorganic chemistry. It's commonplace in photochemistry and many other branches of, say, computational science. So in material science, in biochemistry, and so on. I need to tell right away that electron correlation is not a phenomenon. Phenomenon is, let's say, electronic system. But electron correlation is a concept. It quantifies difference between our approximate description of the system, which is based on mean field usually, and exact description of the same electronic system. And there, the non-dynamic correlation can become very, very important. So if we again try our lovely test animal H2 and try to dissociate it, then we shall see that the energy of the ground state configuration, where two sigma bonding orbitals, sigma G orbitals, doubly occupied, but sigma G orbital is doubly occupied. So this electronic configuration and its energy goes up, up, up as we stretch the bond between distance between the hydrogen atoms. But the energy of the antibonding, doubly excited in this case, electronic configuration goes down until they both meet at some distance. And both potential energy curves for the single determinant built from the lowest symmetry orbitals and from two antibonding orbitals, they are very different from the exact curve. The exact curve, yeah, we have two hydrogens, and as you remember from basic quantum chemistry, energy of hydrogen atom is 1/2 in Hartree units, right? So it should, for two atoms, we should have exactly 1 Hartree or 1 atomic unit at the dissociation limit, of course, -1. But both, they go to very wrong dissociation limit, both energies. Although within narrow range of geometries around the ground state, perturbational theory is still valid, it becomes no longer valid in the dissociation limit. And why is that? Because in the lowest energy correction, second order correction to the energy, so second order contribution to the correlation energy, we have a ratio of two things where the denominator becomes near zero. So we have a difference between, I'll go back to the previous slide. All right. This way. As you see, this would represent Hartree-Fock configuration, and this would represent the doubly excited configuration, their energies become equal. And because of this equality, this and that, the denominator vanishes and the whole perturbation theory simply blows up. Right? This is just a reminder of rules, how to calculate, how to evaluate the matrix elements needed. So energy is just diagonal element of the Hamiltonian, same function. Doubly excited configuration also, same function. And this is cross term between the two states, between the two configurations. And it is actually equal to the so-called exchange integral between, let's say, gerade and ungerade orbitals, so symmetric, anti-symmetric orbitals. So this is a reminder of the ways how we compute these matrix elements, the Slater-Condon rules. They were formulated a long time ago. It's good to have a good idea about these rules. So how to represent the energy of a closed shell determinant, and what is the matrix element between the reference wave function and wave function, or Slater determinant, better to say, where one orbital is replaced by another. So orbital I is replaced by orbital A. In this case, we obtain simply element of the Fock matrix between I and A. And as you remember from maybe, well, I don't know whether you received any course in Hartree-Fock methodology, but in the end of SCF iterations, in the canonical representation of the orbitals I and A, all of diagonal elements supposed to vanish, right? So that's why there are no, provided that the phi node here is a Hartree-Fock wave function, there are no terms corresponding to coupling with single excitations from the Hartree-Fock wave function. And for double excitations, we have another simple expression which involves two electron integrals. You don't have to remember these by heart, because they can be found on the web at many places. You need to simply remember that there are only three types of matrix elements between the single determinant wave functions, which correspond to the same wave function. Well, here I should have added node subscript. Somehow I forgot it. So between same wave function, between single excitation and between double excitation, triple excitation and so on, they will vanish because there are no respective terms in the Hamiltonian to couple more than two particles. So if we now look again at the expression, the perturbational, let's say, expression for the correlation energy of hydrogen molecule, we will see that the energy difference goes rapidly to zero, and at some point it becomes much smaller than the numerator of this. So k, integral k, which is in the numerator, and delta E is in the denominator, right? So approximately at this distance they cross, and therefore, if we can go back to the original expression, if numerator and denominator are equal, then this term will be unity, right? And all other terms, because they are just powers, can be viewed as powers of these, they will also become unity with some constant factor. So that whole perturbational expansion becomes divergent after this point, approximately, even earlier than that. So perturbational treatment of correlation energy is valid only within narrow range of geometries when we have that numerator is much smaller than the denominator in the perturbational terms. And this is not the common case. More common, as we see at stretched geometries of hydrogen, that the denominator becomes very small and numerator is still sufficiently large. So what to do in this case? And some time ago, maybe 60 years ago, a clever way around the problem, or maybe more than 60, because perturbational or quasi-degenerate perturbations theory was formulated quite early on, maybe already in 30s, I don't remember. But it was, let's say, revived when it was necessary to develop some kind of perturbational corrections to multi-configurational wave functions. Well, the basic idea of this quasi-degenerate perturbation theory. All right, we have a situation, for example, where two orbitals become degenerate. This is exactly the case of dissociating H2, where at long distance we have nearly degenerate or exactly degenerate in the dissociation limit sigma G and sigma U orbitals, right? They become degenerate simply. All other orbitals we leave aside. But in the case of two degenerate orbitals, what can we do? How can we develop perturbational theory for system with these properties? In fact, what we need to do is to build electronic configurations corresponding to, let's say, doubly occupied. In this case, I consider that we have an even number of electrons in the system. Doubly occupied configuration with one of the degenerate orbital occupied, then another electronic configuration with the other degenerate orbital occupied, doubly occupied. So this electronic configuration or that electronic configuration, they are labeled here as K and K prime. So this will be the diagonal terms and the off-diagonal terms corresponding to coupling between electronic configurations with doubly occupied this and doubly occupied that orbital. And then we build Hamiltonian, depending on how many degenerate orbitals we have. For the two degenerate orbitals, it will be simple 2 by 2 matrix. Diagonalize it, and we obtain new configurations, electronic configurations, where the degeneracy is resolved. So if we will have, so of course, doubly occupied these, it will be combination of the electronic configurations with doubly occupied this and doubly occupied that orbital, and anti-bonding, out of phase in this case, because these are represent many electron functions. Right, so quasi-degenerate perturbation theory is based on a very simple concept. So we built Hamiltonian matrix involving only degenerate components of the approximate mean field wave function, diagonalize it, and obtain new functions using which we can now build a perturbational theory to describe the rest of the correlation energy. So this diagonalization will, of course, introduce already some energy shift in the, so you can imagine for two electronic configurations, only that the eigenvalue, the lowest eigenvalue, will be below any of these two, and the highest eigenvalue will be above of any of the diagonal terms, diagonal energies here. So this is the concept of quasi-degenerate perturbational theory.
Filatov?
You.
So sorry for interrupting.
No worries.
I have one question about the meaning of the re-optimized orbital by the diagonalization.
In fact, these are not exactly orbitals. I wanted to represent these as electronic configurations. So these are orbitals, okay.
Yes, so if we think about the H2 dissociation case, right, you already explained, then one of the determinants may represent the covalent, and the other may represent ionic.
Exactly. Determinants are always mixtures of covalent and ionic. And covalent and ionic electronic configurations. Only when we construct, say, superposition of the two determinants, we can fully or partly eliminate one or the other contribution. either covalent or ionic.
Yeah, right. My question is by the rediagonalization and the quasi-degenerate perturbation theory, then the how can I say, the configuration will be mixed.
Yes, right.
Then one of tilde may represent the ionic character.
Exactly. Yes, yes, exactly. So in the case of hydrogen molecule, let's say the lowest of these eigenfunctions of this matrix will represent covalent, and the highest will represent the ionic configuration, right? And this will be the energy of the covalent configuration, and this will be energy of the ionic configuration. So this will be, in this case, correct. And or depending, of course, on the distance between the two atoms, this will happen only in the dissociation limit when we can cleanly separate covalent and ionic. In the at the intermediate bond lengths, they will be somehow mixed, but the mixture will be determined variationally, such that to minimize the energy of the lowest state, and in this case, maximize the energy of the higher state. Right, that is correct. So in this way, I tried to represent many electron wave functions. So as if we could, if I put it as a pen, it doesn't work this way. All right, so this will, oh, I had it in fact. So we can put 2 electrons either in one orbital, or we can put 2 electrons in another orbital, right? So this will be one electron configuration, or this will be the other electron configuration, right? So when we diagonalize this matrix, we make one of the electronic configurations. In this case, it will be mixture, of course, of the two Slater determinants. We make it lower energy, and the other will go upper, high in energy. All right, so all that will be done, will be automatically taken over by these simple diagonalization procedures. So I'm explaining these because I will later use this idea about quasi-degenerate perturbation theory in the construction of the method. And because this is also one of the ways to introduce configurational mixing. Imagine that if we have phi k and phi k prime as our two, let's say, ground state, Hartree-Fock, single determinant of hydrogen molecule, and k prime would be our, let's say, doubly excited configuration, electronic configuration. Then we mix them through interaction term. Interaction term will be given by the exchange integral. And we obtain new energies. And the new energies, so that the whole procedure is illustrated here in the next slide. If we apply this quasi-degenerate perturbation theory to our two configurational problem for the hydrogen molecule, so with sigma g orbital doubly occupied or with sigma u orbital doubly occupied, then we will have a simple 2x2 secular problem. So EHF is the energy of this electronic configuration. EAJAB is the energy of this doubly occupied electronic configuration here with doubly occupied sigma u orbital. And K is simply exchange integral between this and that orbital. All right, so that is given by the Slater rules. This is defined by Slater rules, this matrix element between the two electronic configurations. It will be the exchange integral. Building this 2x2 matrix and diagonalizing it, we obtain two new energies. One will be the lowest energy, the first eigenvalue. The other will be, I label it E2 because it corresponds to double excitation. Not single, but double excitation from these. And their energies will be given by, well, we simply can always construct simple quadratic equation for this determinant, for this matrix, and obtain roots of this secular equation in this form. So the form is simply is just solution of a simple quadratic equation. Right? Someone want to ask a question? Or no? All right. So this is simple solution of two-configuration solution of the dissociation problem, in fact. So if we try to apply this energy, which is shown in the previous slide here, to our dissociating hydrogen molecule, we will see that the curve which is produced is essentially exact. So it goes to the exact dissociation limit. Although, while I don't show it here, it may be slightly different in the intermediate region, because some other terms may become also important in near the equilibrium bond length, which will give us the dynamic correlation. But the non-dynamic correlation is correctly captured by this simple 2x2 secular problem. And this is a quite important observation for future derivation of the energy expression within the ensemble DFT. Right, so bond breaking in hydrogen molecule, it's one of the famous examples of course, of the non-dynamic electron correlation, where we need multi-configurational description. And well, although I showed you any expression for the energy, for the ground state energy, as let's say solution of a simple quadratic equation, where it was expressed through energies and coupling terms in some complicated way, it contains square roots of some quantities from the energies. There is a possibility to to express this energy in a very simple form, which involves the so-called occupation numbers of the orbitals. So if we realize that HF configuration, where we have doubly occupied sigma G orbital, is electronic configuration with fixed occupation number, 2 electrons in sigma G, and this is given by electronic configuration with 2 electrons in orbital sigma U. So occupation number of this orbital sigma G is 2 in this configuration, and it is 2 in this configuration of sigma U. So we write from the solution of this equation, you know that we have 2 sets of eigenvalues. In the case of 2 by 2, they are given by sine and cosine of certain angle, but that's not really important for us at the moment. Then we write down the ground state energy, expression for the ground state energy in this form, where we have, well, we can always do that, right? Where we have a square of the first coefficient, and this first coefficient will be given by a square root of the occupation number in the final wave function, occupation number of this orbital, because it gives us the number of electrons that this configuration will have on average, right? The average weight of this configuration. And then we have square of the other coefficient in before the doubly excited energy of the doubly excited configuration. And we will have now some cross term. And if we realize that square, double square, of course, 2, because we have 2 electrons, 2 times this coefficient is average occupation number or fractional occupation number of this orbital in the final many electron, many configurational state. And the other coefficient, square of the other coefficient, is average occupation number, fractional occupation number of sigma U orbital in the many electron wave function, in this ground state wave function. We can, from this energy expression, obtain that energy, where we see that it's average, I mean, weighted sum of energies of ground state electronic configuration with sigma G orbital W occupied.
How do you get this equation? I couldn't follow you.
I simply take eigenvectors of this matrix.
Which matrix? Oh, the 2 by 2.
Yeah, 2 by 2 matrix. And I represented the ground state and the doubly excited state in this way. So these are elements of the eigenvector, the lowest eigenvector of this matrix, which corresponds to E0. Yeah, and these are elements of the eigenvector corresponding to this eigenvalue of the 2 by 2 matrix.
Okay.
So, and in this way, if I substitute this expression into this expansion of the wave function into the energy expression, I obtain this expression for the energy.
So you plug these two vectors into the
into the expectation value of the Hamiltonian, right?
Okay, of ground state.
Yes, for the ground state only. So for these.
So basically, you plug these two vectors into the expectation value of ground state, right?
Right. Yeah. I simply take as this, let's say, phi node tilde H Hamiltonian phi node tilde. So that's what I do here in this, and I plug in this expansion into this matrix, into this expression for the energy. So the energy of the lowest electronic configuration, electronic state in this case.
Okay.
And I obtain this expression. Now what I need to realize, I want to associate these coefficients, squares of these coefficients with average occupation numbers of the respective orbitals. Right? I can view this state, many determinant state, now multi-configurational state, in this case only 2 configurational. I want to view it as state with fractionally occupied orbitals. This is like, well, we can vaguely think of it as if we have Fermi distribution at finite temperature, not at 0 temperature, where it's like a stepwise function, step-like function, and it separates Fermi level, separates occupied and strictly empty states. But if we introduce some finite temperature, pretty high temperature, it should be, and then we will have fractional occupations on average of the orbitals. So it will be difficult to tell which orbitals are empty, which are occupied, but we have now fractional orbital occupation numbers. So
yeah,
they are.
Yeah, this would work in the case of H2, but if you have a more complicated systems,
yes,
you have a lot more.
Yes, that's correct. That's correct.
What would be, that's a kind of becoming approximation or
well, this is only for H2 molecule. In fact, as we will see, at the level of density functional theory, ensemble density functional theory, there are not too many fractionally occupied orbitals that occur.
Yeah.
In the case of standard wave function methodologies, we will have technically at the full CI level all orbitals, I mean, from the lowest to the highest. I mean, even we don't have now unoccupied orbitals at all. All orbitals are occupied. Some are stronger occupied with the occupation numbers closer to 2. Other orbitals are very weakly occupied, occupation numbers near 0, but they are all occupied. So, and this is, I think, important realization in this field, multi-configurational wave functions. It is often used in analysis of the multi-configurational wave functions. So this will be, in the case of CASP-SCF, for example, these occupation numbers will be natural orbital occupation number. They are typically associated with that. But I focus here on a very simple situation, only 2 configurational wave function where interpretation of these occupation numbers is rather simple. On average, I have, let's say, contribution of this configuration with this weight and contribution of this configuration with this weight. And these weights are, because the electronic configurations have this and that have fixed occupation numbers, 2 in sigma u or 2 in sigma g, I can associate these weights with fractional occupations of orbitals, as if these two orbitals were fractionally occupied. This is in some way, let's say, model description, right? But I can always introduce such a concept as fractional occupation numbers of the respective orbitals, right? And in this simple two configurational wave functions, they will be given by the squares of their coefficients of these configurations in the wave function. Or in other words, the energy of the ground state, lowest state, which corresponds to this wave function, will be given by this expression, where I will have kind of weighted sum of the energies of two configurations, with sigma g orbital doubly occupied, this one, and with sigma u orbital doubly occupied. In front of them, I will have, of course, well, in this case, halves of the occupation numbers of the respective orbitals, these fractional occupation numbers. And there will be some coupling term between the two electronic configurations. This coupling term originates from electron-electron interaction, electron-electron repulsion. Yeah, but it is negative because we have solved this equation, and the contribution of this term will have minus sign, right? So it is negative. But this term in front of the weighting factor, in front of the exchange integral, is given by simply by square root of the product of the two fractional occupation numbers, right? So we have the coefficient 2 C node node C2 node. If we realize that each one of them can be represented as square root, we will end up with this expression. I mean, that square root of ng is square root of 2 times C node node, and square root of nu is square root of 2 times C2 node.